Okay, thanks a lot for the introduction, Alex. Thanks a lot for the invitation to all the organizers. Yeah, I'll talk about two papers written this summer in collaboration with Eric Doka, Carlos Mafra, and Boris Piolin. And one of the reasons, apart from the scientific fit, is that I chose to talk about this is that these two papers are actually an outgrowth of this conference series. I mean, last year's edition took place at UCLA, a few meters away from Eric's office. So I dare to say last year's meeting was important to bring this collaboration together. Okay, so this is about a string perturbation theory. And let me give a try to summarize where we are right now on string amplitudes. I'm sure the slide is going to bring me into diplomatic trouble, so I should add as many disclaimers as possible to what you find on that slide and what not. So here I want to give an overview of which string amplitudes are available in a form that you can get numbers out of them, that you can really stick in numerical values into the polarizations and momenta, at least order by order in alpha prime, to convert them into a number. So without loss of generality, I'll be around in the type 2 theory and scatter gravitons and their supersymmetry partners. Okay, so what do we have? On one axis, you have the loop order or the genus in string perturbation theory. And here on that axis, we go for more and more external legs. Starting at genus 0, we are in more than good shape at 4 points. This is, if you wish, the birth of string theory by the work of Gabriele in '68. But also for an arbitrary number of master states, we have good formulas that are friendly for evaluation for n open and closed string tree-level amplitudes. So all the kinematics boils down to field theory amplitudes, Young, Mills, trees, or the respective double copies. And also the integrals are understood in the alpha prime expansion. Good, that's it for tree level. Let's look at one loop. So here is one milestone by Brink, Green, and Schwartz in '82 that also Julio was mentioning. So we know it from this one loop string theory calculation that maximal supergravity enjoys the no triangle property. The 4-point loop amplitude in maximal supergravity has the box graph only, namely with 0 powers of loop momentum upstairs. And we know this from strings, so from this work of Michael and collaborators. So what about higher multiplicity versions of this? Okay, so depending on what you look for, one difficult task in string loop amplitudes is to manifest the supersymmetry cancellations of bosons versus fermions in the loop. And this, for instance, comes about from the RNS spin structures. So for the spin sums, there has been a very beautiful method by Tsuchiya, which does them for any number of external bosons. But maybe you also want to have the external fermions, and maybe you also want to be in a logarithmic form. So what I mean by that? Well, practitioners of CHY and conventional string amplitudes love the Park-Taylor forms at tree level because they have logarithmic singularities. And there's a relatively sharp notion of what it means to be a logarithmic form in genus 1. So yeah, as to such logarithmic forms, the frontier is at 7 points, and we hope to move on for this. But this talk is about 2 loops, so I should go on in this field. So for 2 loops, the magical year was 2005. I'm even given the month of the appearance of the key papers. So it started with Doker and Fong computing the 4-point function in the RNS formalism. They arrived at a neat result that I will review shortly. And that result was also recomputed using the pure spinor formalism and supersymmetrized in the sense that here from Berkowitz and Berkowitz-Mafra, you find the first fermionic statements. And this talk will essentially be about the 5-point version thereof, along with a variety of corollaries in the field theory limit, including a BCJ representation of the field theory amplitudes. But before getting there, it's important to highlight the record. So clearly the chip leaders in that business are Humberto Gomez and Carlos Mafra, who did a 3-loop 4-point calculation in 2013, or more precisely, they worked out the low energy limit of the 4-point functions. And yeah, this was motivated by some S-duality prediction for t to the 6th, r to the 4th. And the calculation was a big success to reproduce that duality prediction from the amplitude prescription. Yeah, so that's it for the context/history. Let me now come to the two-loop 5-point region of that diagram. So given that we know the 4-point function for a very long time already, I think I owe you a solid reason why the hell we are doing 5 points now. So what's the extra value? What does 5 points have, what 4 point doesn't? So first of all, for the main topic of this conference, so 5 points is the first non-trivial showcase of color kinematics in action for the two-loop amplitudes. I mean, two-loop 4 points is a little bit too simple to appreciate the BCJ duality there. We really need to go to 5 points to see loop momenta in the numerator and to see interplay between different diagrams, specifically pentaboxes and double boxes. Yeah, more on this later in this talk. Another line of motivation, pro 5 point, is, it has been nicely explained in the talk of Michael Green. This has to do with the U1R symmetry of type 2b supergravity, which is broken by string corrections. Okay, Michael was talking about this phenomenon on the gauge side of the ADS-CFT dictionary. But as far as the gravity amplitudes in type 2b superstrings are concerned, they can violate U1 symmetry, but only at 5 points and beyond. As Michael was alluding to, these are particularly simple amplitudes, and we definitely need a 5-point calculation to have access to those. So that's part of the results we could discuss in our two-loop papers. Some more motivation. What else is great about 5 points? This is a rather mathematical motivation. So the alpha prime expansion of closed string amplitudes are a beautiful laboratory to explore the universe of non-holomorphic modular forms. So this is known under the name of modular graph functions. Majority of the literature is about genus 1, but there is a growing body of results on higher genus modular graph functions, which were pioneered in these two beautiful papers by Eric, by Michael, and by Boris. And we learned a lot about higher genus modular graph forms when we dissected the 5-point function, something that the 4-point function per se doesn't give you easily. So we learned about a mechanism to generate algebraic relations between modular graph functions. And we furthermore learned that they in fact want to be generalized to tensors. So at genus greater than 1, the modular graph things actually want to be modular graph tensors. So this you can read about in a recent paper with Eric. Okay, and last but not least, coming back to the diagram of multi-loop, multi-leg, one of the things you can learn from two-loop 5 points is how you can deal with zero-mode contractions between left and right movers. And this zero-mode pattern was the engine of the calculation of Humberto and Carlos at 3 loops. So in a vague sense, two-loop 5 points is a little bit like 3-loop 4 points. So since we on the long run want to move up in loop order, it's important that we get multi-leg results, say at 2 loops, to be prepared for the new kinds of zero-mode patterns that are waiting for us. Yeah, so this is the motivation. Let me now come to the main body of this talk. I'll start with a hopefully gentle review of the 4-point results from 2005. Then I will explain one of the key methods, the so-called chiral splitting formalism, which introduces loop momenta into string amplitudes and which also have some beautiful implications on the existence of global integrands in field theory. And then section 3 is the main part where I present the results from the papers. Yeah, any urgent question about the structure and flow of logic? Then let's get into business. Let's look at two-loop 4 points. So this is a summary of the results obtained by Do-Kor-Fong as well as Berkowitz and Berkowitz-Mafra. Yeah, we have this two-loop 4-point closed string amplitude for external gravitons. And here's first of all a good message about the tensor structure. If you know the tree-level amplitudes, then you will immediately have the tensor structure under control. Namely, it's this famous T8 tensor contracting 4 powers of the linearized field strength. So this is the story for external bosons, and there's a well-studied supersymmetrization. Just look it up in tree level. Okay, so this is taking care of all the polarizations, and we don't need to talk about them anymore. the rest of our energy will go into this scalar integral coming along with that. Yeah, let me try to walk you piece by piece through the different ingredients of that scalar integral here. We integrate, among other things, over punctures, over 4 punctures placed on this genus 2 worldsheet. So here the informal notation is sigma to the 4th, meaning that there is Z1, Z2, Z3, Z4 to integrate over. I'll introduce the objects in the integrand shortly, but let me prior to this tell you about the other integral in the first line. So this is about the shape of the genus 2 surface. This is about the complex structure moduli that are here parametrized by period matrices omega, symmetric 2x2 matrices. So this is integrated over the moduli space of those. Yeah, this is the to-do list in that scalar integral. And let me give you more details about the integrand. So one of them is an evergreen, this Kober-Nielsen factor. It appears whenever you have plane waves in the vertex operators. You can immediately say that you get exponentiated Green's functions for all pairs of external legs. So here we have the Green's function at genus G. So instead of giving you the full glory definition, let me just wave my hands and tell you that for sure you know it at tree level, where it is the logarithm. And the entire genus, you need to make sure it fits to the periodicity properties as you send your punctures around the homology cycles. So you can use theta functions and prime forms and so on to represent this, but we won't need the explicit form. Okay, so Kober-Nielsen is definitely there. And now it's time to lift the secret about these mysterious deltas. So maybe you already missed to see a d square z for the integration measure. Well, since we are beyond genus 1, it's a little bit more subtle. There is not just a single dz, but for each puncture, there is an entire vector of possible differentials. So omega I are the 2 holomorphic differentials on a genus 2 surface. So what these deltas are antisymmetric combinations of these multiple incarnations of dz. So you can say that this holomorphic square of the deltas is the 2-loop version of all the d square z's, taking into account that you have more than one holomorphic differential now. And yeah, amusingly, these differentials are antisymmetrized. So here the definition of delta as an epsilon tensor. So it's an antisymmetric quantity under swapping the 2 entries, which has some fun implications. Okay, now I told you about the things that do occur in the integrand, but maybe it's more interesting to talk about what's not there. There is not a single singularity as the punctures go together. There's nothing singular as you get with 2 punctures very close together. And as a result, you don't have any chance to generate a tree-level propagator. I mean, these tree-level propagators come from short-distance singularities, which are not there. So whatever the field theory limit is, it won't have any tree-level diagrams. It won't have any triangle box like here. It will for sure not have this kind of bubble type diagram. Good, so this is stuff we see on the spot from the absence of singularities. As you see, I'm already transitioning to describe the field theory limit to you. So let's now take a closer look. What is the connection to Feynman integrals? Well, we are starting with an integral over period matrices. And these period matrices, they become in the field theory limit some measure for world-line skeleton diagrams. So the moduli space integral becomes a Schwinger parameter integral over the different lengths, L1, L2, L3, of the lines in the world-line skeleton diagram. So this degeneration is known under the name of tropical limit, very beautifully explained, for instance, in this paper of Piotr. And yeah, so what you land on in the alpha prime to 0 limit, you really land on the Schwinger parametrization of double box integrals, both the planar and the non-planar ones. And here's one more refined statement. So here is a fun story concerning these deltas, these anti-symmetrized combinations of the holomorphic differentials. So in the field theory limit, these holomorphic differentials, they become constant on the world line graph. Sorry that I'm not giving you more details about these omegas, but I don't think you need to know more apart from the fact that they are constant along the world line graph, if they not vanish by themselves. And this means that these deltas, they don't want that the two insertions are on the same world line edge. So these deltas, if you wish, filters, they kick out field theory graphs. They don't want that too many punctures accumulate on the same edge of the world line skeleton. So it's the virtue of these deltas that, for instance, you don't have these penta triangles or more exotic graphs. Okay, so this is an old story revisited, why the two-loop four-point functions are so simple, why there are only double boxes.
About 5 minutes left, Ollie.
Thank you. Yeah, let's get a bit closer to the 5-point zone. We will compute these 5-point functions in the framework of chiral splitting. So this is about introducing loop momenta into string amplitudes. You may wonder where the loop momenta are if string amplitudes are normally about integrating moduli. But yeah, so these loop momenta, they come from certain zero modes of the worldsheet fields. Zero modes that are computed on certain cycles. So here you make a choice of, say, preferring the A cycles over the B cycles. And loop momenta, as you know from field theory, they may jump by external momenta if you're not careful. So for instance, if you send your punctures around the B cycle, then this will mean that your A cycle measuring the loop momenta catches an extra loop. So if you're not careful, you catch shifts in the loop momenta. And I think we all agree that we don't want that. We want to have a globally defined loop integrand. So let's make sure that the move of walking around the B cycle is forbidden. What's the formalized way of forbidding the cycles from walking around the B cycle? The magic word is a canonical dissection. You cut open the Riemann surface along the A and B cycles, meeting at a specific point. So this is a little bit like choosing a reference frame. So if you want to have a globally defined loop momentum, if you want to have a global notion of a field theory integrand, you should work on such a canonical dissection. You may have aesthetic caveats about that. It's far away from manifest modular invariance, but what it definitely gives you is a global loop integrand in field theory. So I felt that this fact is a bit under-acknowledged. That's why I'm reviewing this key result of Piotr's beautiful paper. Okay, I hope I got some of your sympathy in favor of chiral splitting, but let me now come to the main reason why it's a good idea to use chiral splitting for string amplitudes. So there is a mild coupling between left and right movers through the loop momenta, since these are the zero modes of the left movers dx, but also of the right movers d bar x. So since there's a shared zero mode of left and right movers, they couple if you path integrate over the zero mode. So let's better not path integrate. Let's instead outsource this zero mode integral and leave it to the last step. And as a reward, you get an honest factorization between left and right movers. They stop talking to each other in the moment that you work at fixed loop momentum. So the strategy is to compute the chiral amplitude at fixed loop momentum, which is a purely open string quantity. So the leftover job in computing the two-loop 5-point function is to determine the chiral amplitude f5, which is an open string problem. So if you want to see an example for such chiral amplitudes, the 4-point guy is right here. Remember, I was introducing this T8 tensor for the polarizations, and these deltas anti-symmetrized combinations of holomorphic differentials. And there's also a version of the Kober-Nielsen factor that takes chiral splitting into account and where you do see some loop momenta in the exponent. All right, so let's get to work for the 5-point chiral amplitude. We saw that we just need to perform an open string calculation to achieve the goal of this talk, to present the two-loop 5-point amplitudes of the closed string. So let's see, what is the upgrade of the 4-point result? So there were these deltas that I kept on highlighting, which you can trace back to certain zero mode games in the pure spinor formalism. And the same kind of zero mode rules, they still apply at 5 points, but you have a little bit more space to play with the zero modes. you have enough space to pick up a loop momentum from the vertex operators. And also, you have enough space to perform an OPE and to catch a single singularity. So you can get tree-level propagators at 5 points. Okay, so now apart from the deltas known from 4 points and caused by zero modes, there is a little bit more space for an extra holomorphic differential. So this is the collection of 5 forms that appear in the 5-point chiral amplitude. And if you have a collection of forms, why not go to a basis? And it's an easy exercise in group theory to find a 5-element basis. So when stripping off the forms, there are only 5 zero forms left to compute where all the kinematics are sitting. So this chiral amplitude decomposes into what we call a subcorrelator, where all the polarizations are sitting and where all the form degrees of freedom are gone. All right. So how do we compute the subcorrelators of the chiral amplitude? In view of the time constraints, maybe I skip the slide and you can ask me later, but I think I should by all means show you the result. So the chiral amplitude is, as I said, it has loop momentum, a single power for the chiral one, and a second power coming from the complex conjugate in the closed string amplitude. And there is something with OPE singularities. So this is, if you wish, just a version of 1 over Z2 minus Z1. Okay, so these are the objects in the subcorrelator, and we have kinematics. These are certain superfields. So in the first place, we are doing this in pure spinor superspace, where you can grab any combination of external bosons and fermions. But since I want to deliver you the bosonic expressions without taking you into pure spinor superspace, let me promise you that you get all of these guys by simple combinations of T8 and epsilon 10 tensors. So there's no hidden agenda apart from the formula you see on these slides. If you patiently stick them into each other, you have everything fully explicit, the complete subcorrelator, and therefore the complete chiral amplitude. Okay, in the remaining minus n minutes, I think I should say a few words about the field theory limit. So as we already know from JJ and Henrik from their work in 2011, there are only 6 different diagram topologies, and the planar pentabox can be taken to be the master under kinematic Jacobi identities. So let's, to keep it simple, just give you a sample how to compute the pentabox numerator from our chiral amplitude. So as you saw before, it is expanded in terms of certain 5 forms with a funny gadget delta. Yeah, antisymmetric in the pairs of insertions, and they don't want Z2 and Z3 to be on the same branch of the world line skeleton. So by choosing a particular pentabox, you have a collection of deltas that vanishes, and therefore 4 out of the 5 subcorrelators die. So the entire pentabox numerator comes from a single subcorrelator, and you just need to track how the different bits and pieces therein behave if you go with alpha prime to 0 and if you go to the tropical degeneration of the Riemann surface. They are constant. They are just plus minus I pi. So all this to say, you get a pretty tame expression for the pentabox numerator. Okay, here, these are once more our pure spinor superfields. There is a vectorial superfield T vector missing. My apologies for that. It's precisely that guy that you're supposed to, insert down to the numerator. And each of them, as I said before, is a simple combination of T8 and epsilon 10. Yeah, I'm really torturing the chairman. I should wrap up. So if you compute the remaining diagrams, you also find that they satisfy all kinematic Jacobi relations. So this is another showcase that the alpha prime to 0 limit of string amplitudes tends to give you BCJ representations, now established at 2 loop 5 points. Yeah, so you saw a crash course on chiral splitting in this talk, advertising to introduce loop momenta in intermediate steps of a string theory calculation, where you reduce all the hard work to a chiral half to an open string problem. The kinematics at 2 loop 5 points are T8 and epsilon 10 plus supersymmetrizations. And yeah, the process of doing the field theory limit is known as tropical degenerations. You can ask more to Piotr or to any of me and my co-authors from the papers. Yeah, that's it. Thanks for your patience.
Thank you, Ollie, for that nice talk. Do we have any quick questions before we call an end to the main proceedings for the day and break off into groups? Lance?
Hey, Oliver, thanks for that talk. So when you said on your first slide you were going to present things for where you could get numbers out, you just mean numbers for integrands, right?
Oh, okay. Caveat number 1, it's numbers order by order in alpha prime. And okay, let's say at
But
tree
do you
level
have that for the 2 loop 5 point case? Numbers order by order in alpha prime after integrating over all the moduli and the locations of the vertex operators and subtracting the field theory contributions?
to leading and the subleading order in alpha prime. Leading order is in the end the volume of the moduli space. And at the subleading order, it's the integral over the so-called Chanka-Bazumi invariant, where mathematicians were saying 7 years ago that this is impossible to compute. But it was actually computed in 2014 by, who was it? Eric and Boris and Michael and Rodolfo. Yeah, so we know it at the subleading order in the 2 loop 4 point and 5 point function.
So how do you do the infrared subtraction at 2 loop 5 point? How do you remove all the non-analytic terms that come from the massless field theory?
Oh, okay. Is this something I can walk you through in a 1 loop context, or is your question specifically geared at 2 loops?
Yeah, I guess you could do 1 loop, yeah.
Okay. So in the 1 loop 4 point function already, there are indeed a lot of branch cut singularities coming from the boundary of moduli space where tau is very large. So at the cusp where the torus degenerates. Yeah, so the non-analytic part coming from the cusp can on the one hand be determined by unitarity. Also, you can use some recent tools developed by Eric and Michael where they have, I think, all order results on the non-analytic term. So this is isolating the contribution from the cusp, the discontinuity. Then you can run a separate calculation in the bulk of moduli space at finite tau, where you do the Z integrals order by order in alpha prime and use the machinery of modular graph functions. And yet another challenge is to patch these two things together. So this is yet another hard part.
But now you also have poles in the 5 point case when 2 vertices collide, which you didn't have in the 4 point case, correct?
Okay, it's correct that these are extra poles not present at 4 points, yeah. But I dare to say these poles don't cause any extra complication with respect to the separation into analytic versus non-analytic.
Okay.
The way how you can disarm them goes as follows. You can do integration by parts on the worldsheet to go to a basis of integrals that are non-singular. So whenever a pole has an integral has such a pole, there are enough IBPs to express it in terms of non-singular integrals. And then you just perform the analysis at the level of the non-singular integrals. It is slightly harder at 4 points because you have derivatives of the Green's functions, but I can force these derivatives of the Green's functions to not line up, to not give you a double pole in when the punctures collide.